Good afternoon, everyone. Thank you for joining us today. My name is Marissa Waterman. I'm the Marketing Director here at AAEES. Here with us today, we have Rick Czekanski, I hope I said that right, a Senior Associate at Remington and Vernick Engineers. Today, we'll be discussing water reclamation facility expansion project in Logan Township, New Jersey. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, you'll be able to type your question into the attendee chat panel on the left-hand side of your screen. We'll also share email address of the speaker, Rick, so you can email him directly with additional questions you may have. Okay, let's get started. Good morning, Rick. Thank you for joining us, and we're ready when you are.
Hi, nice of you all to be here today. I'm Rick Czekanski, Remington and Vernick Engineers. We have an office here in Cherry Hill, New Jersey. We're located just outside Philadelphia. And what you've seen on your screen, you may not know it, but you had a preview of our presentation today. The slide that was in the lower left, the piping that was shown, that's a slide later in our presentation that deals with the sequencing batch reactor tank that we're going to talk about. All right, so a little bit about myself. We'll switch here to the slides. And as Marissa talked about, we're lucky enough as a company to win the design category last year for the Logan Township MUA 0.5 MGD water reclamation facility expansion. Logan Township itself is located just on the New Jersey side of the Delaware River from Philadelphia. Myself, I've worked on plants anywhere from size from 500,000 gallons all the way up to 90 million gallons per day. I've had a lot of multi-discipline interaction with different people in our company over the 30 years I've been here at Remington and Vernick, where I've been the manager of the structural, environmental, mechanical, electrical, plumbing, and water wastewater groups in my career here. So let's talk about the project in general. What you're here to hear about today is that in New Jersey, you have to develop a wastewater management plan to determine what will be your plant flow before you can actually design it. You just can't go and say, today I'm going to design a 5 MGD plant and start going. It won't be approved. So there's a study done that determines ultimate build out, which excludes land that has environmental constraints. In the case of Logan, they determined was 2.75 MGD was their ultimate. Currently at the plant, they had a capacity of 2 million gallons, so they decided to be proactive. At that time, the flow was averaging about 1.2 MGD when we started this design, and now it's only got up to 1.4. They thought it'd be a little more accelerated, but that's where we are today. Again, we have that wastewater management plan step, but also what we have in New Jersey is that once you reach 90% of your average daily flow, you also have to provide the DEP report that talks about when you get to your ultimate flow, what's going to happen, what's your plan, what's your expansion. So talk a little bit about the current facilities there, and I'll try to tie this together with a site map so you have a better understanding. The current facilities, as we started, had a bar screen, aerated grid tank, a lift pump station, into an equalization tank. Now that equalization tank because the capacity was 2 MGD, it was almost half the average daily flow of the plant at the time. It has that storage capability. So from that tank, there was a valving system that would allow the flow to go to 2 contact stabilization tanks. And there was also a mini pump station that when 2 existing sequencing batch reactors, I'm going to say that a lot today, or SBRs, when they're in their idle mode and they're ready to accept new flow, those pumps kick on and we can treat that 0.5 MGD. From those tanks, they have effluent piping that is combined to go into a discharge itself, goes into effluent lagoons, and from there, there's filtration and another lift pump station that's sent with a outfall that's about 3 miles long that sends it out to the Delaware River, which is a wide body river just outside Philadelphia. So what did we add? And I'll show you this in an upcoming slide. We added a retaining wall at the back end of the site because we're very land limited. We added a larger sequential batch reactor. We call it SBR number 3, where again, you see the dimensions, 122 by 50 by 22.5. And as it says there, that's 8 feet higher than the 2 SBRs they have now. Again, going back on the other slide, the existing SBRs are only 74-foot diameter. This is much larger size. Because we have additional equipment, additional electrical panels, we enlarged the control building. As you can see, we enlarged it from 20.5 feet deep, almost up to 54 feet deep or long, and we also doubled the height of the building. Because we're adding a lot of larger motors, the existing service and the existing generator could not take the load, so we had to bring in a new service and a new 1500 kW generator. So this is the site post-construction. And just to give you an idea, just to look at the whole area here, we have water everywhere, all 3 sides of the plant. And this water is associated with wetlands at the site. And it also establishes that this control building here, the floor of this building at elevation 10 was a 100-year flood elevation. So that actually had an effect on our design. We had to make sure everything we did was a foot higher than this 100-year flood elevation. So just to start with some of the tank process, things that I've talked about on previous slides, the bar screen, your area to grid tank, that lift pump station's all off the picture. This is the equalization tank. This is the intermediate pump station where there's some valving in there. They'll send flow to the contact stabilization tank here or here. And there's 2 pumps in there that will, again, when these existing 2 SBR tanks, when one of them has gone through all its phases and is idling, will send flow into the control building, and the flow is basically by use of motorized valves, will either go to this tank or this tank, again, whatever one is idling. At the very back end of the site, I'm going to talk about a retaining wall we built in order to fit all this in. And from this view, looking this way, left to right, you'll see this tank number 1 in several slides we have today as this whole project progressed. So pre-design, we're trying to figure out and work with the DEP as to where we can put our new tankage. So all this land is available to Logan Township Municipal Utility Authority, but the site plan I just showed you was this area here, again, turn 90 degrees. This white area was pre-designed with the wetlands buffer area. So you even see that some of the existing facilities are already in the wetlands buffer. So again, this is pre-design condition. So talking with the DEP, they were going to take more And on this particular side, which had a 50-foot wetlands buffer, they wanted 150 feet wetlands buffer because conditions changed. And this area here in blue was all that was left to us to put additional tankage. Well, we in New Jersey are allowed to have pre-permitting meetings, and through that pre-permitting meeting, we had a secondary meeting to talk about this whole issue with the DEP at the plant. And through these discussions, we provided them some different options, whether we could put a circular SBR down here, a rectangular one here. Again, 2 other circular SBRs here. As you see, alternatives 3 and 4, that would be possible options. So the DEP has priorities, Logan Township has priorities, and we're all trying to work these out. From water and wetlands constraints, we can't be constructing within wetlands, but we can possibly construct within wetlands buffer. There's also habitat in the area for eagles, and the fear from the DEP and the wildlife people was that if we put a freestanding Sbr tank all by itself, one of these eagles may fly into the tanks. If we got rid of any trees within a wetlands buffer area, we had to compensate for that. So the vegetative constraint. And there's operational constraints where the MUA would prefer to have any tankage in close proximity to the control building. And lastly, we're talking to the DEP in regards to they're assuming in their regulations that any wetlands buffer area must be undisturbed. And we're saying that a treatment plant is probably totally disturbed. So why can't we put tanks anywhere we want? So based on all this cooperation from the DEP, we were able to come to certain agreements. One, that we have to protect the adjacent wetlands, and that's what we're talking about. The back of the site, we have to put a retaining wall to level out our grades, but also prohibit us from going into that wetlands area. Alternatives 1 and 2 that you saw before, which were the circle and the rectangle that were near the control building, we are permitted to put the tanks in that wetlands buffer area. We'll be getting rid of 10 pine trees in that area, so we had to do compensation planting. And again, from Logan Township's point of view, this was the best alternative right adjacent to their control building. And everything about being undisturbed soil sort of went by the wayside once all these decisions were made. So we have to design the tanks. Tanks have to be designed based on certain criteria. And the most important one was the BOD, or biochemical oxygen demand, BOD5. In an average community, the BOD5 may be 160 milligrams per liter. But at Logan Township, because they were receiving a lot of food processing waste from commercial areas within town, commercial industrial areas, we had to design the tank for 600 milligrams per liter. And just to give you an idea, the recent data said that they're averaging now 652. We're also designing for total suspended solids. The average community in New Jersey is about 200 milligrams per liter. You see Logan Township in 2021 had an average of 700. The design was based on 600. The ammonia was, I would say, average for any community, coming in at 40 milligrams per liter, but they had an advantage that they could discharge at 35 milligrams per liter because they're going to a wide water body, the Delaware River. However, in our design criteria, we required that the SBR be able to discharge at 2 milligrams per liter in the event anything in this permit changed in the future. And at the very bottom, there's a chemical oxygen demand. And we'll talk about the effect that that had on some of the design later on in a later slide. So we're going about this And we're starting our design. We have locations. We didn't know if we were going to have a circular SBR, rectangular SBR. We have a narrow strip of land that's, again, maybe 60 feet wide, 60 to 75 feet wide in order to put all these facilities. And the decision was made to speed up the process is to pre-purchase some of the equipment. And this, we didn't know it at the time, but that was a tremendous advantage following this path, because what happened was, instead of calling a manufacturer on the phone trying to get information out of them, when the job was awarded to Avoca Water Technology, they were very cooperative information with the information they would provide, and I'll mention some of that as we go along in this presentation. But also, we were able to design as we're looking at shop drawings and figuring out how everything fit together. So the Sbr tank equipment, a lot of that is fiberglass piping. 2 centrifugal blowers. Currently at the plant, they have 2 SBRs, but only 2 blowers. So what happens is that when one tank needs aeration, the other tank has to be in another cycle. There's a piece of equipment called the jet motive pump that we're going to see later on that handles the recirculation within the Sbr tank. And so Logan wanted security for future operations in case something went down in their pump. With their pump, they wanted a whole spare pump plus an impeller. And you'll see how this information is very helpful when we get to some slides that are, when you see some of the piping arrangements, you'll see that something couldn't be described over the phone. So when we bid the project, these are how the costs were separated by the contractor. We're going to talk about the retaining wall. We're going to talk about the ground improvement elements. We're going to talk about tank number 3. We're going to talk about costs associated and things that went on in the equipment building. Talked about the intermediate pump station already. That's when the flow is sent to the SBR, and what we did there, the flow coming into SBR, and each SBR is about 2,000 gallons per minute. We increased the impellers to increase the total dynamic head capability of those pumps, because the new SBR, again, is 8 foot higher than in elevation and in height than the other existing SBRs. So we got a $5.6 million project here, plus the other $500,000 or so you saw from the pre-purchase bid. So again, even though it's only 3% of the work, let's show you something about it. And this is the first view of the views I was talking about that will come up certain times in this presentation, and you can see how things changed over time. When we started, you see that the site slowly slopes to the back, slowly slopes to a lot of where this water is and vegetation and wetlands line. And you see the 10 pine trees here that had to be compensated for in another part of the land that the authority owns. So contractor trenched out for the retaining wall. Just to give you some background here, what you're looking at for that reinforcing on our drawings, it would say that it's number 4s, which each one of the numbers corresponds to an 1/8 of an inch diameter. So it's number 4s at 9 inches on center, top and bottom, each way. That's what you're looking at there. And when the slab is poured, the slab is going to be 1 foot thick. So as we moved along the site and the grade increased, we didn't need to construct a retaining wall that was as deep or as high. So we used a step construction for the foundation. And once poured, that looks like this. Again, the rebars that are now in the vertical are going to connect to the wall that's going up. And those are number 4s at 9 inches on center in the vertical. And all those red caps that are there are protective vices. If a worker comes along and trips on one of those boards or trips and he falls on the rebar, they're, again, protective devices so he doesn't get as injured. And here's just a view of the formwork before the concrete is poured. But you can see how the concrete was poured with a pumper truck in order to reach the whole length of the wall. Let's talk about the Sbr tank itself. And again, that was the large rectangular tank that you saw in one of the slides. Again, I'll use Sbr, I'll say sequential batch reactor, it's all the same thing. Oops, went the wrong way. So we're back to our view again. And after those pine trees are gone, the contractor's cleaning up the site. And again, we're going to show you how the site changes over time, or this view changes over time. So how do these rectangular tanks work? Most treatment plants have aeration tanks followed by settling tanks, but the sequential batch reactor does that all within one footprint. How does it do that? Flow comes in, it starts filling up the tank, and basically for the case that we have where the tank is about 22.5 feet high, we're only talking about filling the top 4 feet. The rest of the 18.5 feet is the mixed liquor in the tank that keeps the process going. So we're filling up the top 4 feet. We're in the aeration mode where we're reacting. After sufficient dissolved oxygens in the system and the operators feel they have sufficient treatment, the aeration stops. And we have a settlement stage. The sludge settles to the bottom. So now that sludge is settled to the bottom, we have a clear liquid for the top 4 feet. This device here, which we'll detail later in the slide, and in fact represents the very first picture we talked about for this presentation. That was in the lower left-hand corner of your cover sheet there. This is called the decanter, and when a automatic or motorized butterfly valve opens here, the water goes through the system and it'll go ultimate to the effluent lagoons. And after the water goes down and we've drained that 4 feet of active area or active zone, the Sbr now is in the idle stage. Occasionally the operator will reverse some of the piping and reverse the flow in the waste sludge system. I'll talk about how the flow is reversed later on. He has to get rid of some of the waste sludge. And it's sitting there waiting for the PLC system to say, let's fill again, and we're going to activate that pump that's in the intermediate pump station. So we're starting to construct the tank. You saw that they were clearing land, but we have bad soils. We're near water. That sends a big flag that be careful. So based on information we had, based on soil borings, our company designed what was called the CGE system, which is CGE stands for Cast in Place Ground Improvement Element. And what these are very similar to piles, only we're not banging piles into the ground. We're drilling holes into the ground. And in fact, for the original plan for this Sbr was to drill 286 14-inch diameter, 65-ton capacity CGEs that would be 50 feet deep. Now, one benefit to the authority came about in this whole process is that the sub who was going to install all this came up with an alternative plan that through value engineering was accepted, but our company reviewed it. It was accepted by the owner, and the owner received a credit for a reduction in number of CGEs based on greater capacity and increased space. So here's what they look like at the surface. Pile caps aren't required. It just basically stays like this. And these grouted rods provide the ground support. Again, the advantage here is that we have no vibration as opposed to banging in piles. So due to that vibration, we don't have all this additional possible consolidation of the surrounding soils, which might cause settlement somewhere else in the plant. So below the CGEs are even on the very edges of the tank. And above this is a picture of the beginning of the foundation for the Sbr tank itself. Remember, it's 122 feet long, 50 feet wide, pretty sizable. And again, we're trying to fit it into a very small stretch of land. So we're right up against the retaining wall on this side. And eventually the contractor installs his reinforcing and sets his forms for the concrete pour, which eventually is poured. And to show you how it looks on the other side, again, we're using almost every foot we can. We're right up against one of the other Sbr tanks. So this is the beginning of the foundation being established. Here's a view of the overall tank as work is progressing. Contractor eventually puts in 6 inches of stone, puts a vapor barrier above the stone, and then the contractor starts installing the reinforcing rods that he was going to use for the Sbr slab itself. This is more of a completed picture, as we talked about before. You have certain spacing of the rebar, top and bottom, each way, the way it's expressed. And there's the tank once, the slab once it's poured. So things change now. So we're done with base slabs, and we're talking about how do we erect the walls. Well, we made a decision during the design, as opposed to having all that reinforcing sticking up in the air, just like you saw for the retaining wall, that we would go to what's called a precast post-tension reinforced concrete slab structure. There was a sub that was provided for this by the contractor. It was Dutchland Industries. They're located in Pennsylvania. And the way they make these slabs, which become slabs that are then converted to the walls, is that they pour them at their facility. There's a minimum 2-week cure time there. But right after they pour them, about 14 hours afterward, they use high-strength concrete, a high-early concrete, that they break some cylinders, and they determine when they get to 2,500 PSI, they take the forms off those slabs and they start using them on other slabs. The overall idea is not to accumulate slabs at their facility, but to take these slabs, get them on a truck, and as soon as they're ready to be transported, bring them to a site such as this, hook them up right to the crane, and have them installed. So where this slab is going to fit is in this 5-inch groove that's already established in the base slab, waiting for it. The contractor's erecting these slabs, and this one, particular one here, shows several slabs that are together, and they're installing a walkway on top of those slabs, and we'll come to these holes later. That's where some of the tension wires are going to go through. And the slab construction continues. All these braces that are inside this tank here, that's what keeps everything erect. At the very bottom here, they're actually anchored to the slab. They're just like not a broomstick that are leaning against the wall, but they're actually providing a service to keeping all these slabs erect. Then we still have joints in the slabs, and in those joints, a Sika product, Sika Flex 1A, is put in, and that's an elastomeric sealant. So as these slabs, as we talk about later, they're going to move a little bit when the wires are put through those holes. There's a hydraulic jack that pulls the wires. These slabs are going to move a little bit. So that's why this sealant is an elastomeric one, to be able to take that change in position. So we're getting close to the completion of the slab work all the way around the perimeter of the tank. And once we do, the wires are put through. Again, a hydraulic jack is used to pull those wires. The other thing that happened with this one, when the concrete was poured at Dutchland's facility, they had an additive that was included, so we didn't have to paint the interior of these tanks. Remember, there was a high chemical oxygen demand, and we're afraid that that might have an effect on the concrete long term. So we had an additive put in the tank in order to prevent corrosion. So the wires in the pull with the jack, there's anchors on the other end. And then in addition to the Sika product that's between all these joints and at the bottom, there's a 5,000 PSI grout that's added also to make the tank watertight. Let me go back here. Let me go back here and I'll talk a little bit about the water tightness test. So if you remember, we had effluent lagoons that these SBRs were discharging into. We allowed the contractor to take water out of those lagoons and fill up this tank. And the testing criteria was that once this tank was filled, there would be no moisture spots shown on the outside of the surface. If there was, the contractor had to do a grout repair. So the criteria was, it was a max loss of 0.05% per 24-hour period. And when the water level went down 3/8 of an inch, the test was complete. So he had to meet all that criteria. And at the same time, a rain gauge had to be installed in case it rained, and that would be part of the compensation. And also there was calculations done for evaporation. So all that was taken into account. But of course, right now, the tank is watertight and passes tests. Oops. All right, so here's a view outside the tank. And this is the effluent pipe for the tank. It's heat traced and insulated because we have a motorized valve right here that when it opens, that's when that decanter will let the water out of the tank. These electrical conduits here are related to lights that are on top of the SBR, but they're also related to dissolved oxygen, ORP instrumentation, and high water floats. High water float sends an alarm to the plant that the water has exceeded the designated fill elevation that was supposed to stop the intermediate pump station pumps from discharging. On the other side of the tank, what we have here is a stairway that's put in because we have to access it. Landings themselves are based on OSHA requirements with landing every designated vertical feet. And down the bottom here, we have the control building over here. And what happens is there's two 20-inch pipes that are associated with the jet motive pump to recirculate flow in this direction. And we also have a 6-inch drain that comes out of this direction. Those 20-inch pipes neck down to 16-inch, and the 20-inch pipes were used that we had to upsize them a little bit because, again, we went out for pre-purchase for those pumps. And then once we got into final design, we saw we had to make some adjustments in the pipe diameters to make sure all the hydraulics worked. So that the 20-inch pipe necks down to 16. And what you're seeing here is the beginning of the pipe installation after the tank passed its water tightness test. This top pipe here is an air pipe. This next one here is providing recirculated water. This is a jet nozzle, with the idea being that you'll see a diagram in a second, that this air pipe combines with the water in this pipe to send it out the jet nozzles, which instead of stainless steel diffusers that you might see in some aeration tanks, this is the means of providing this tank with dissolved oxygen. So these two pipes themselves are 16-inch. This is actually the fill pipe for the tank, that when the tank's in the fill mode, this extends to about halfway across the tank. This is just a picture of one half of the tank. You can see the spacing with those jet nozzles. The tank is sloped to the center to try to get the, again, when the tank is empty, we can get all the water to the drain and be able to empty the tank if need be. So here's the diagram I was talking about in regards to mixing air with the recirculated water. And one of the important aspects of working with Evoqua during the shop drawing process and asking questions and everything else is that there's 17 feet of loss that had to be included in the total dynamic head of our jet motive pump, which is supplying this recirculated water. So it's important to have those discussions. It's important to realize that you always have a loss with the diffuser. And again, communication is key. So this is the picture that was on the cover sheet at the beginning of this presentation. This again is called the Decanter. This, along with that piping, is fiberglass. It's used to remove the treated water for, again, in this case, the top 4 feet of the tank. And it swivels based on this flexible coupling here. Outside the wall is our motorized butterfly valve that, if this tank was full and that butterfly valve open, would allow the water to come out and go to the effluent lagoons. So here's a partially filled tank. This is probably the beginning of the construction. We're looking at the jet nozzle operation. You can see that they're all working. The decanter itself is on a support system here. And so when the water level rises, this decanter will float up with it. Now I have to take the flow, get into my decanter, have it go by the butterfly valve, combine it with the effluent piping for the other SBRs, and get the water to the effluent lagoons. In order to do that, this is a wet tap that was made in the yard area just prior to the effluent lagoons. So we have a 16-inch pipe here. We have a 16-inch gate valve here. And you usually don't see something unusual about this. This is the sleeve for the wet tap itself. This is a flange-flange connection, but on this side of the gate valve, it's a mechanical joint. So this pipe here is able to deflect a little bit due to soil conditions. What you see here is actually the device that's used to create the wet tap itself. So with a 16-inch pipe, we're actually going to make a 16-inch diameter hole on the side of this pipe. This device here is going to hook to that, what they call the coupon, and then remove that coupon through the valve. And as it's removing that coupon through the valve will close, and this whole operation is, they call it drip tight. We had a previous job years ago. Unfortunately, that coupon was lost in a force main, and it hasn't affected the operation of that pump station yet, but I think 99 out of 100 times they probably bring the coupons out, which certainly makes everybody feel better about that. So we have an animation here. We showed you in the beginning the different cycles of the SBR operation. We just go over those again. So here we are in the idle position, and we have to add flow to the tank. And what I described previously is that if this is our fill pipe, in the case of our Logan Township, that fill pipe ends about halfway, and that's where all the water comes out. This is the recirculation pipe, and this is the air pipe here. So we're in the fill cycle. The decanter floats up. It's on its flexible coupling. It's in the react stage now. This is a typical aeration tank, aeration mode. We're now going to settle the sludge to the bottom. And now we're to decant the clearer treated liquid from the top by opening the butterfly valve here. And again, this is all controlled by a PLC. So it's fill, react, settle, decant, and then goes to idle. So let's talk about another improvement that was made. We had the existing control building, we doubled the height, and we increased the length almost 2.5 times for this building. And this is the completed construction, but we have different views inside this building. So this is what I call the front of the building. Of course, this will be the back. The blowers are located on this side of the building, and the jet motive pump and the piping is located on this side. So ideally, when Logan Township, the MUA, was looking initially to have a tank in close proximity, this was all ideal to them. And remember that the floor itself is right at the 100-year flood elevation. So we're going to take a look at from the front of the existing building the way it looked before. And when you walked into the building the way it looked before, you saw 2 blowers. Okay. Again, I have 2 tanks. If one of these blowers was out, they had to rely on one blower that would send, if the left blower was out, they would rely on the right blower to send the flow across to the Sbr tank on that side. But again, all the tanks had to be in different phases for this to work. And this basically is the outside wall that you're looking at right in front of you. This is the other view. This is a view from the other way, from the way things looked outside that wall. So here's the air filter for each of the 2 blowers. And here's the blower piping, again with that interconnections on the other side of the wall. These pipes that are here are associated with the recirculation of flow for the jet motive pumps. And the piping up top here is the Decanter piping for each of these tanks. They combine somewhere in this building, go down and out to the effluent lagoon. So this is the beginning of the demolition for this building, but again, we have an active wastewater treatment plant that must stay in operation. So in our specifications, Remington and Vernick had a maintenance of plant operation spec, which identified 12 different shutdowns that were required in order to fulfill or build all the facilities you're looking at today. So most of those shutdowns occurred in this existing building. And what it talked about is that the contractor would give a schedule as to when he needed that shutdown. He would give advance warning to the owner. The owner would either allow it or deny the shutdown to occur on that specific time. Usually what would happen is that the owner was running equipment manually as things were shifted over, say, to the new revised upgraded control system or valving change. And also what happened with the control system is that we had to rewire all the existing automated control valves with the existing Sbr system. There was 4 to 5 motorized valves with each Sbr. So that all had to be performed. And again, those Sbrs were kept operational while this was going on. So you can see the building itself, I believe, was only 20 feet deep in the beginning. We're going to 53 feet. These pads here were blower pads. This is a pad for the jet motive pumps. Again, the 2 air filters are here. And as this whole building is being enlarged, we also said to the contractor, there was a garage door here. Once the building is enlarged, you have to be able to let a free flow of air come in so these blowers continue to work. We always needed either an opening in the roof, garage doors open, or something to that effect to give us that free flow of air. So that building stayed there by itself as we built around it. And again, the work continues. You can see how the existing facilities remained operational as, again, the work was continuing. So here's a view from the ground level, and we're looking at from the rear of the building, or still looking at what remains of the original building construction. I have my pre-purchased blowers over here on the left. I have rebar here on the bottom that's waiting for the concrete to be poured. We have a pre-purchased jet motive pump over here. And this is a view months later. I have my blowers on the left. I have my jet motive pump, but I have a lot of piping that's going on over here associated with this whole jet motive pumps and the recirculation of flow. And notice the traveling bridge above, which was included in order to help the operators move equipment around if they need be. So we'll say this is one of my favorite views. This is a view back from the front of the building, looking to the rear. What you're seeing on the ground here is not like liquid that might have spilled on the ground, but actually what these two squares are, or rectangles, are the original locations of the two blowers that you saw previously. Here's brown here is about the outside wall. Here's the two blowers that have now been moved over there. So again, this jet motive pump, it's called a vertical centrifugal pump, and it was part of the pre-purchase equipment. So you always got to remember when you pre-purchase something, or because you are handing this equipment to a contractor, you want to make sure it's correct. If you were looking from the air, this is our plan view. This is the pipe that's providing the new flow from the intermediate pump station that has a connection into this pump. So if you're looking from a plan view, it might be entering from 12 o'clock and the discharge is at 3. When we check the pre-purchased equipment, this incoming pipe was at 9 and going out at 3. So Avoca had to come back, take that pump away, and provide us another pump. What you're seeing here is this pump has a capacity of 5,900 gallons a minute. It's got a 29 feet total dynamic head. Unusual for pump design is that it has no static head because it's taking flow to and from a tank. And basically the tank level is the same when it's suctioning from the tank and delivering back from the tank. This is a 60 horsepower premium efficiency motor, and even though this pump was replaced, we had a certified pump test taken at the factory to make sure it was representative. The flow and head was confirmed before this was delivered to the site. So I'm going to show you a view looking this way now of all this piping. And this is what I said earlier. It's very difficult to describe this kind of piping over the phone. This is some of the recirculation piping, and I'll give you another diagram as to what it all means. But again, when flow comes into the Sbr tank, it follows this path right through here. It goes directly into the tank and not through the pump itself. There's another T over here for waste sludge. That'll eventually, and this is the waste sludge connection over here. So this was one of the advantages of having the pre-purchase contract, working with Avoca and be able to understand what pipe sizes I need, their orientation, and how to be able to fit them in. So all that piping I just showed you, here's a diagram of it, even though it showed, I want to say opposite hand, a lot of this piping is really on the other side at Logan Township. But what happens is, I showed you the jet aerators before, the discharge from this pump goes to that pipe that's just below the air lines that combines to send the flow out. It's combined with the air to send the flow out and have my 17 feet of loss, and it aerates the tank. And then from the fill line that's associated with this tank, that pulls water in to here, and that's recirculated this way during normal operation when we're in the reactor aeration stage. But it's recommended at least once a day that you clean your jet diffusers. So what happens is we have to reverse the flow. So we're taking a reverse flow. The suction is now, instead of going out of the jet diffusers, it's coming through the jet diffusers, and by automatically opening, close, well, I think this is manually, on some of these valves is that the flow comes in to the suction of the pump and is discharged out the fill pipe, which is like a free discharge. So that's this circulation package, this circulation pattern continues, but again, the flow is reversed through the jet nozzles to keep them clean. On the other side of the room, we have our two pre-purchased blowers. We have our two relocated blowers, and all this was done during, again, relocating these blowers was done under certain criteria as to how the owner kept the plant operating. The existing blowers here, they have 60 horsepower motors. The large ones here, 125. These pre-purchased blowers are 1440 SCFM. Notice that everything is raised about a foot above the floor because I got 100-year flood hazard elevation down here. Over here, the owner wanted future room in case he replaced these blowers someday. In the event he was thinking about he may someday raise the walls on his existing SBRs, get more treatment capacity. And then there's a lot of valves and piping over here because now the existing SBRs have a backup. We have 3 Sbr tanks, we have 4 blowers. So either of these blowers can be a backup to either a new Sbr blower or the existing blowers. And right here you notice some couplings that were put in, so vibration from the blowers don't affect the piping systems. Since I showed you the air filters for the existing blowers previously, the 2 that are inside the building, we just showed you where they're located now. This panel on the left is the automatic transfer switch for the emergency generator outside. This is a motor control center for all these large horsepower pumps and motors that we've been talking about. And also, the authority got a new control system. I'm told this is more of a preliminary type of layout that they were that they had received, and it's more advanced at this point. Here's the 4 blowers here. Talked about different manifolding of the piping system, opening and closing different valves to allow the pre-purchased blowers to be able to support or back up the other blowers. You can see that the SBRs themselves are in different sequences. 2 are in react, 1's in fill. The one existing SBR can fill up to 14.5 feet. It's almost there, but it's in the react stage. So it didn't make it all the way to the 14.5 feet, but the water in there is getting treatment. This is a mixed fill. So it's at a lower elevation, so it has to go from 11 up to 14.5 when it's filled. And the new SBR at 22.5 feet basically is what filled to, is that when it's in the react stage, and actually the water level can actually rise anywhere from 1 inch to 6 inch. In this particular case, the operators are looking at the dissolved oxygen. I was told that the ORP meters weren't registering right at this time, but you can see this particular SBR here has a 0 dissolved oxygen, which I'm told during the fill stage it doesn't operate. So in addition to having a new control scheme in their control building, what we also did was get 2 laptops for the operators where they can take their computers or laptops home and they can operate the plant from home if something happens at night. They don't have to run out to the plant. They can check what's going on from home. So just to show you some of the information and the construction of the emergency generator. This is the fuel tank for the emergency generator. It's got a 24-hour capacity. The owner prefers this type of housing over the generator, where if he's doing work on a generator, he's protected entirely from the elements. And again, I have to be a foot higher than 100-year flood elevation, which I am right here. And it looks like a very nice facility with the stairways going up, going into those doors. It has a very nice appearance. So we're back to where we started. And where we started was the view of the 10 pine trees. So 10 pine trees have now been replaced by an emergency generator and a large Sbr tank. Way back here, we have that automated butterfly valve with my piping that's sending the flow out to the effluent lagoons. I have an air pipe that's coming in, and we saw how that connects into the top pipe of the Sbr unit. We have the stairway with landing at specific locations. We have 20-inch piping that's coming up here. In this particular instance, is heat traced and insulated, and it reduces to 16-inch before it gets into the tank. And we have our generator, and off to the side here, we have a switch gear and a transformer, which is part of the new service. So, getting close to the end here, the time for completion for this whole project was 450 days. It extended longer than that. There were interactions between the owner and the contractor that the owner wasn't going to pay everything, pay full until everything was done to his satisfaction. We had the design and shop drawing review portion of this project. We didn't do the inspection, so there might be specific questions you have in construction, which I may or may not be able to answer, but I can find the answer to. The final payment again, it was awarded for $5.6 million. The final payment was $231,000 below that, which if you told any client that I'm going to do a project for you and there won't be any change orders above what you want awarded for, I'm sure that client would be very happy. So Logan Township was happy with this project also. I'd like to thank the authority for the Academy, saying authority too much in this presentation. The Academy for allowing us to present this, and also to the Logan Township MUA staff, Chris Whalen, the superintendent, and his staff for the cooperation they showed during design and the whole construction period. There's my email address. I'd like to thank everybody for participating and watching this presentation. And again, to introduce yourself to Remington Vernick Engineers, we have offices throughout the Mid-Atlantic area, a large engineering company, and you can see the type of work that we can do.
Excellent. Thank you so much. We appreciate it, Rick. Now we'll open up for questions. If you have a question, just type it in on the left-hand side of your screen where it says attendee chat, and we'll try our best to answer all the questions. And if you prefer, like Rick said, feel free to email him directly. I see there's already a few questions. You can just get started and read them off and answer them as you go.
Hi, everybody. How were the pressure drop reduced during transmission? I'm assuming for the blowers themselves, when you do blower calculations, 90 to 95% of the loss is basically the water level in the tank. There's very little loss in the piping systems if you have the right velocities and the right pipe sizes. For the jet motive pump, by enlarging the diameter from 16 to 20 inches, we decrease the friction and minor losses in that tank, in that piping system, in order to fit the TDH that we use for the pre-purchase bid. What happens there is that when you're looking at a diagram from equipment manufacturer, there's a tank and they have the pump right next to the tank. Well, we were 50, 60, 80 feet away, and we had, again, to account for those losses in that 60, 80 feet of piping, and you saw how a lot of it looked like spaghetti. Basically, you had to account for it to make sure everything worked correctly. What type of tanks are those? Is it fixed roof or floating roof? There is no there is no roof on the SBRs themselves. Basically, it was what the client was looking for because he already had 2 SBRs. His operators were trained in their operation. What authorities like is familiarity with their operators, so they're not, don't want to necessarily introduce a new process. We keep things uniform. Again, due to change in personnel, you don't want to be training people all the time on a bunch of different systems. They already had a contact stabilization tanks there and the 2 SBRs. So, plus we were really deficient or lacked a lot of room in order to put these facilities in. So they didn't necessarily have roofs on them. There was no roofs on the tanks. Was there any criteria like selection of this kind of tank? Was not performed on the pipeline or ascertained prospective leak points. I don't believe that there was any test done on the fiberglass piping within the tank. However, the buried piping was pressure tested. Now they're a few years out of construction. Were there any issues with the Eagles? Haven't heard of any. Just haven't been informed that there was any issues at all, but it was a concern to the wildlife people at the time. What innovations do you need to add to your SBR to meet nutrient requirements for river discharge? Well, on one of the slides, you saw the overall ammonia limit. Well, the overall ammonia limit in the permit right now was, I believe, 35 milligrams per liter. Common in New Jersey, discharging to a smaller stream is 2 to 5. That SBR, the new one, was supposed to operate 2 or below. And what it said on the slide was the overall plant performance is 2.6 in, say, 2021. So I'm not sure which tank was the cause to be elevated over 2. What's happening in a lot of cases is that possible phosphorus removal may come in the future. There was a partial test for that at the plant, but we didn't have a limit set. We just wanted to make sure that it could start the process. Typically, even with the nitrification, you can't partially nitrify. That you have to be sort of all in. So that's what I could tell you about that. Right now, they don't have any hint that their permit might be changing, but they were looking ahead. Excellent example of how a wastewater treatment plant project in a small community can move complex than those in a large community. The strong and highly variable wastewaters from the food processors make things especially interesting. Nice job. Yes, it's true. You have to look at different parameters you're faced with. One time in the past on the New Jersey Turnpike, we did the design for one of the service areas. Well, it ended up that the ammonia in that case was 160 milligrams per liter. A lot of people are going to the rest stop, using the bathroom facilities and moving on. That posed another set of problems. Again, you have to look at what you have in front of you and investigate that it's true, it exists, and then do your design from there. Just don't cookie cutter and assume everything's the same. How are you able to successfully negotiate your regulator support necessary construction of wetlands buffer zone? That was all through their cooperation. Our company had worked with a lot of these reviewers for years. And again, we had the pre-application meeting. We then had a meeting at the plant. Again, it was their wildlife people who were talking about the concerns about the eagles. they could see by putting a tank out there by themselves, how difficult it would be possibly for controlling it and how it would disrupt the effluent lagoons. So it was all through cooperation. And basically, you see from one slide to the other, part of it might have been that in one part of the plant, we had a 50-foot buffer, but when the job was finished, we had a 150-foot buffer everywhere, and we basically had to take that plan with meets and bounds on the buffer line, and it was filed in the county courthouse as, you know, this is like deed restricted. So it was all through cooperation with the DEP. What was the time period between the pre-purchase equipment and construction? Any certain storage equipment maintenance concerns during that period? There was a gap in time. I can't tell you exactly what it was. It probably was could have been as longer than 6 months to a year. In the specifications, you do talk that the equipment should be prepackaged for long-term use, or long-term storage rather, as their spare jet motor pump is right now. The fiberglass pipe itself, it really, the concern is there, probably keep it out of the sunlight. I don't know if it's affected like PVC pipe is, but basically it's the equipment was indoors, the blowers were indoors, the pump was indoors. It's all instructions provided from the manufacturer that they may occasionally have to go in there to grease something. Tell us more about your value engineer alternative plan for less CGEs, and how many were you able to reduce the number by? I think the number actually, it's not our design again. The subcontractor came in, and I don't know the details for the CGE design, but I know that if we said that the ones we designed were 75 tons, I think they went to 90 tons. I think the spacing was 5 feet. They went to 8 feet, and they may have cut the number almost in half, but they were able to prove, again, I don't know the specific calculations for CGEs, but they were able to prove that they still had the coverage needed. And I don't know the exact number, but the owner probably benefited by $30,000 to $50,000.
Excellent. Thank you so much, everyone, for all your questions. We're going to wrap up for today. If anyone has any additional questions, please feel free to email Richard directly. His email is somewhere in the chat there. I typed it in a few minutes ago. Our next webinar, titled Environmental Justice at EPA, will take place on Wednesday, July 20th. Please go to aaees.org/events to reserve your spot. And if you're not yet a member of AAES and would like to learn more, please email me at mwaterman@aaees.org, and I can send you all of our membership options. Again, thank you so much. Thank you, Rick, for your time today, and thank you, everyone, for attending. Have a great afternoon.
Thank you, everybody.
Bye-bye.